Hello, everyone. I'm Yibo, a PhD student at UT Austin. Today, I'm going to talk about our recent work, Tigon, a distributed database for a CXL pod. First, I'd like to start with a problem that has been studied for decades: how to efficiently scale out a transactional database from a single node to multiple nodes. As shown in the left figure, one way is to partition the data and store them in each host. This is the most common approach. The advantage of this approach is that it scales really well for transactions that touch only a single partition. However, when executing transactions that touch multiple partitions, this approach will incur numerous message exchanges and will require an expensive two-phase commit protocol to guarantee transaction semantics. Another approach, as shown in the right figure, is to store all data in remote shared memory enabled by the RDMA technology. The advantage of this approach is that there is no message exchange or two-phase commit. However, it suffers from the microsecond latency of RDMA operations and high programming complexity, as RDMA relies on specialized interfaces and drivers. So, what is the root cause for their bad performance? Well, the root cause is their use of a network for synchronizing cross-host data accesses. Specifically, for databases who partition data across hosts, they rely on message passing over a network to access data stored on other hosts and to handle concurrency. For databases who store data in RDMA remote shared memory, they rely on RDMA operations to access data and to synchronize concurrent accesses. As a result, these two operations either suffer from numerous message exchanges or high latency remote memory access, both introduced by the network. A natural question is, can we avoid using a network for cross-host data synchronization? The answer is yes. The emerging CXL, or Compute Express Link technology, provides a new opportunity for doing cross-host data synchronization. CXL is a high-performance, open standard interconnect between CPUs and devices based on PCIe. A CXL memory is a memory module connected to one or multiple hosts via CXL over PCIe bus. The first use case of CXL memory is to use it as a memory expansion, which introduces a new tier of memory and enables memory pooling. A lot of recent work focuses on system software moving memory pages between local and CXL memory on behalf of applications. The second use case of CXL memory, as shown on the right side, is to use it as an inter-host shared memory connected to multiple hosts, which is our focus. Specifically, we are interested in a new hardware setup called CXL pod. A CXL pod consists of a set of hosts connected to a shared CXL memory module. Each host in a CXL pod has its own CPUs and DRAM, and it shares access to the CXL memory module. CXL supports inter-host hardware cache coherence based on CXL 3.0 and the most recent 3.2 specification. Although today's hardware, such as Niagara 2.0 from SK Hynix, does not support hardware cache coherence, we believe future hardware will support it. Compared with RDMA, CXL had three advantages: lower latency, hundreds of nanoseconds, CPU load and store instructions, and inter-host hardware cache coherence. So we find a CXL pod really fascinating because it is an intermediate configuration between a fully distributed system and a shared memory system. On the one hand, it is a distributed system in that it consists of multiple hosts, so we can run a database on multiple nodes. On the other hand, it is a shared memory system in that now there is an inter-host shared memory connected to multiple hosts. And the most exciting thing about this inter-host shared memory is that now we can avoid using a network and instead use inter-host atomic instructions and hardware cache coherence to synchronize cross-host data accesses. So how do we scale out a database on multiple nodes? Here are two naive approaches. Let's first look at the left figure. Similar to the partition-based shared nothing architecture, one approach is to partition the data and use CXL memory to transfer messages between hosts. For example, we can put a message queue in CXL memory and let each host use it to send and receive messages. In our evaluation, we found that this approach yields at most 2 times higher throughput for the TPC-C workload, which is great. However, this approach still incurs numerous message exchanges and require two-phase commit for multi-partition transactions. The second approach is to store everything in CXL. In this approach, every host can access all data and can use inter-host atomic instructions and hardware cache coherence for data synchronization, avoiding message exchange and two-phase commit. This seems like a better design. However, does it work? It doesn't work because CXL memory has 2 major limitations. Firstly, CXL has worse performance than DRAM. It has higher latency and lower bandwidth. So this means that we cannot simply put all data in CXL memory if we want to achieve peak performance. In other words, we need to leverage high-performance local DRAM. Secondly, due to the hardware overhead for maintaining inter-host cache coherence, CXL pod will support only a small size of the hardware cache coherent region. You can imagine that you have a terabytes of CXL memory with only tens of hundreds of megabytes being hardware cache coherent. This means we must minimize the usage of hardware cache coherent memory. We propose Tigon, the first transactional in-memory database for a CXL pod. To solve the challenges of CXL memory, Tigon adopts a partition and shared architecture called Pasha. There are 2 big ideas. The first idea is to leverage the high-performance local DRAM. Tigon partitions the data and stores them in local DRAM, like a partition database. Secondly, to minimize hardware cache coherent memory usage, while still being able to avoid message passing and two-phase commit like a shared memory database, Tigon shares only the data that will be accessed by multiple hosts in CXL memory. More specifically, Tigon initially partitions the data and stores them in the local DRAM of each host. If a host wants to access the data stored in a remote partition, it will send a data movement request asking the remote host to move that data to CXL memory. Compared with the 2 naive approaches we discussed earlier, Tigon reduces the number of message exchanges by exchanging messages only for data movement and avoids two-phase commit by moving remotely accessed data to CXL memory. And finally, since the size of CXL memory is limited, Tigon will move data back to its original partition when CXL memory is full. Next, I will talk about the technical challenges of Tigon and how we address them. The first challenge of Tigon is reducing data movement frequency. The key problem here is that if we store all data in a hardware cache coherent region only, then Tigon will incur frequent data movement because the hardware cache coherent region is oversubscribed. Therefore, to minimize hardware cache coherence usage, Tigon stores data in the CXL region that is not hardware cache coherent. Then, Tigon uses a software cache coherence protocol to enable cacheable access to the non-hardware cache coherent region. The key ideas here are to first compact the synchronization heavy and software cache coherence metadata into 8 bytes and store them in the hardware cache coherent region. Then we use that metadata to enable coherent and cacheable access to the non-hardware cache coherent region. Our results show that when running YCSB as the workload, Tigon with software cache coherence enabled is 5 times faster than storing data in hardware cache coherent region only, due to avoiding frequent data movement. Another challenge Tigon addresses is avoiding two-phase commit. The key problem here is how to let each host execute and lock all transaction operations on its own. In Tigon, transaction execution involves 3 database operations: tuple modifications, index operations, and data movements. Our key insight is that the last 2 operations, index operations and data movements, modifies only the internal state of a database, which can be reconstructed or simply discarded upon recovery. So there's no need to lock these operations. Therefore, during transaction execution, Tigon lets the remote host move data so that each host can execute all tuple modifications. Tigon then adapts value logging that logs tuple modifications only. Upon recovery, Tigon reconstructs indexes and data movement metadata. So now I'm gonna walk you through sort of a toy example to give you a sense of how Tigon works in practice. Here, we have 2 hosts, each running a transaction. Initially, all data are stored in local partitions, and nothing is moved to CXL. First, transaction 1 running a host 1 wants to read A. Since A is in local DRAM, transaction 1 directly logs and reads it. Then, transaction 1 wants to write C, but C is currently stored in host 2's DRAM. So it sends a data movement request to host 2, saying, hey, can you move C to CXL memory? What host 2 does is that it moves C to CXL memory and inserts it to the index in CXL memory so that host 1 can find it. Now, transaction 1 can directly access C in CXL memory. It will take a write lock because it wants to do a write and then update C to a new value, 9. Finally, let's say now transaction 2 wants to read C. Since C is moved to CXL, transaction 2 will go check the tuple in CXL memory and finds it already locked by transaction 1 and aborts itself. So by working this toy example, I'm trying to tell you 2 takeaways. Firstly, each host can execute all tuple modifications for a single transaction, avoiding two-phase commit. And this is achieved by Tigon moving remotely accessed data to CXL memory. And secondly, Tigon maintains only data that is accessed by multiple hosts in shared CXL memory, minimizing the usage of hardware cache coherent memory. Now let's look at some performance numbers. For evaluation setup, since the real CXL pod hardware is not commercially available, we emulate a CXL pod using a single 40-core physical machine connected to a CXL 1.1 memory module. We run 8 VMs, each with 5 cores, to emulate a pod with 8 hosts. We compare Tigon with 2 partition-based in-memory databases, Sundial and DS2PL. Sundial adopts an optimistic concurrency control protocol, while DS2PL adopts two-phase locking. For fair comparison, we further improve these 2 baselines by replacing their network transport with CXL message queues. And again, by repurposing a network thread originally used for sending network messages for transaction execution. We call these improved baselines Sundial Plus and DS2PL Plus. Finally, we also compare Tigon with Motor, a recent RDMA-based shared memory database. Here are the results of TPC-C. In the x-axis, we vary the percentages of multi-partition transactions, and in the y-axis, we report the corresponding throughput. Since the default configuration of TPC-C is to have 10% of new order and 15% of payment transactions being remote, we vary these 2 ratios proportionally. We first showed results of Sundial and DS2PL. We can see that their performance drops as the percentages of multi-partition transactions increase, This is because they adopt a partitioned and shared nothing architecture, and therefore suffers from the overhead of numerous message exchanges and two-phase commit. We then showed results of Motor. Motor's throughput remains stable. However, its performance suffers because of the overhead of high latency one-sided RDMA operations. Finally, we showed results of Tigon. Tigon is at most 75% and 2.4 times faster than optimized versions of Sundial and DS2PL. This is because Tigon reduces the number of message passing and avoids two-phase commit. Compared with Motor, Tigon is 11 to 14 times faster. This is because CXL is much faster than RDMA, and also because Tigon avoids storing everything in CXL memory. In the last experiment, we want to understand how the size of hardware cache coherence would impact the performance of Tigon. So we vary the size of hardware cache coherence budget from 200 megabytes to 10 megabytes, and run TPC-C and YCSB. For TPC-C, as shown on the left figure, with a 60-90 multi-partition transaction percentage, it is encouraging that the performance drop is within 8% for 50 to 150 megabytes, and 24% for 10 megabytes. And this is because TPC-C has only 2 tables that will be accessed by multiple hosts. And the hardware cache coherence budget is large enough for Tigon to hold most of that data in CXL, reducing the frequency of data movement. Now let's look at the right figure. The results show that YCSB requires 100 megabytes to achieve full performance. With 50 megabytes, the throughput drops by 60%. With 10 megabytes, the drop is 80%. This is because YCSB has only a single table, and every data tuple in that table has a probability of being remotely accessed. In the worst case, where we have only 10 megabytes hardware cache coherence budget, Tigon moves 110K tuples every second, significantly increasing transaction latency because now transactions have to wait for data movement operations to complete. To summarize, in this talk, we proposed a new direction for building distributed databases. Instead of doing distributed synchronization over a network, let's do it over shared CXL memory, utilizing the emerging CXL technology. Following this direction, we built Tigon, the first distributed transactional in-memory database for a CXL pod. To address the hardware challenges of CXL, Tigon adopts the partial architecture that partitions data in local DRAM and shares only the data that is remotely accessed in CXL. Tigon then minimizes hardware cache coherence usage using a software cache coherence protocol. And finally, Tigon avoids two-phase commit by adopting value logging and reconstructing internal state upon recovery. Thank you.